Hello everyone, my name is Muna Aman and I'm one of the TAs for Introduction to Deep Learning course for Fall 2025. In the previous video, we saw how data loaders and dataset classes are developed. So the next step is to know how to perform data preprocessing. Here we're going to see how to perform signal preprocessing and image preprocessing. So, why is it important? Why data preprocessing is important? Data preprocessing is considered one of the important machine learning steps in machine learning pipeline. So, the raw data is usually noisy and inconsistent, and it has irrelevant information. This pre-processing, it helps us to transform these raw data to more clean and standardized format. It also enhances the feature quality, so the model only learns about the important features that it needs to see. It also reduces the risk of overfitting and also improves the speed and stability of the model. So we need it to ensure that our model receives only the high quality and relevant features. So we're moving on to signal preprocessing. When for signal preprocessing, we can think about it when we hear someone talking, our brain doesn't just process these raw sound waves. It actually like picks the meaningful features like the pitch, like the tone, like the phonetic information. So our machine learning model also need to only extract these meaningful features. And as we mentioned that the problem with the raw audio file, let's think about for signal. We have a 2-second clip sampled at 16 gigahertz, which is standard rate. When we multiply 2 seconds by 16 gigahertz, it will give us 32,000 data points. And we can see that this will form a challenge. First, it's going to be very computationally expensive to process all of this data. And also, the raw audio is usually noisy, so our model is going to be sensitive to noise. And also, there is no structure, which means that the waveform, it will not just like capture the important information that we need, like the linguistic information. So we need to perform feature extraction. So one of the most important pre-processing technique for speech is male frequency separal coefficients, the MFCCs. Why are they important? First, they have perceptual relevance. So what that means that they are based on the Mel scale. The Mel scale is that it mimics like how the humans perceive the sound. And also it performs dimensionality reduction. So we end up with only like 12 to 13 coefficients per time frame. And also MFCCs are less sensitive to noise or variations in the recording conditions. So we can move on to see our code. So we're going to start by importing the libraries, which is like okay, yeah, here. So we're going to start by importing the libraries, the torch audio. We're also going to use a library called the librosa, and we're going to see how all this fits in together. Okay. In the second cell, here we're just downloading some audio files from a LibreSpeech dataset. We're using wget, which is it helps us download the data set from online. and we're only downloading dataset which has like a subtract of one or two. Okay, then here we define an audio path. This audio path is just a path for a single audio file. It's always good to listen to your raw data. Is if it's images, you need to see the image before doing any transformation. If it's audio, it's good to listen to the audio before doing any transformations. So we can listen to this audio.
That it has a broad measure of truth, though the word exactly might seem an overstatement.
Okay. So this is a raw audio file. From here, we move on. So first, we load the audio file. We're going to use the Librosa library that we mentioned earlier. It's going to load the audio file from the audio path that we specified. And here we're setting the sampling rate to none, which means that it keeps the original sampling rate. It's not going to do a resample. Okay. Here wwave waveform.shape. It tells how many audio samples are in the signal. We also print other information which shows us how many data points per second are used to represent this audio. Here we want to get the length of the audio file. So we just define the length of the waveform by the sampling rate. This helps us to find the duration of the audio in seconds. So it helps us to know if it's like 10 seconds, 16 seconds audio, and then we print this information. We also visualize the raw audio form just to waveform to know how it looks like. Okay, so we printed all the information that we need. And we also get to see how the raw audio waveform looks like. It's the x-axis is the time and the y-axis is the amplitude. So the first step we're going to perform is transforming this raw audio file to Mel spectrogram. The Mel spectrogram, like this representation of the audio energy at various time. Um, we do this to first to visualize the audio content over time and frequency, and then when we want to calculate the MFCCs, we need to have the Mel spectrogram. So this first line here, we also using the Librosa library, and we were just like we're using this line to get the Mel spectrogram. Uh, the second one here, we are it gives us the spectrogram values, which are like originally energy or power. So we convert it to the decibel scale, which makes the value easier to like interpret visually. So we do this and then we visualize how the Mel spectrogram looks like. So this is the time and this is the frequency domain. We move on to calculate the MFCCs. For the MFCCs, as we said, these are like further process features is derived from the Mel spectrogram by like applying a specific operations. We do this because we said the MFCCs reduces the dimensionality, and it also makes it closer to how humans preserve the sounds. So here we're also using the museum library. This line just help us to calculate the MFCC's features. We're getting the first 14 features in each audio file, and then we can print it. We can also see how the transformation is done over the time. So domain, and this is the MFCCs. Okay. Then we used to do an operation called substral normalization, which is a process of scaling the MFCCs. So they have like a mean of zero or all of them to get all of them centered around zero. So we do this just to make sure that all features contribute equally to the model learning. Okay, here we compute the mean of the FCCs over the SCD, and then we're just going to add like a small amount of number here just to avoid the division by zero. And then we can visualize it to see how it looks like after the normalization. Yeah, so it's time and then is the normalized, again, the normalized MFCCs. And we use the color scale to see if all of them should be like centered around zero. So the color should be like around here. This visualization help us to understand if all the features are now normalized and centered around zero. Okay, now we have our MFCCs. We move on to the next step of the pre-processing, which is the augmentation. The augmentation, we use it to reduce the overfitting and improve the robustness of the model. So it's less sensitive to the noise or like the partial loss of information. So we are going to do two two operations. The first call is time masking. So as we said, sometimes is like a partial loss is going to happen. Is either in time or frequency or like think about it. If you have an audio and then like 2 seconds of the audio are missing, like the network just falls out and then you don't hear anymore, and then you hear the person again. So if we don't do this segmentation, if we train a model with only full audio, when this happens, when this drop happens, the model is going to be less accurate. So that's why we do these things because it happens in real life. So the first one is time masking. Yeah, so this line here, we're using it to perform the time masking. We set the maximum lengths of possible, like the possible lengths, to 100. And then 20% is the proportion of the time axis that can be masked. Okay, and then we're just transferring to tensor. Tensors is how PyTorch chooses to use to like the format PyTorch chooses to process files. Then we can plot it here. We can see here, this is where our audio dropped, like this time, where we perform the time masking. And second, we perform something called also like the frequency masking. And here we're setting the maximum width to 5. And then we are performing the frequency masking on the with width of 5. Okay, so all what we saw before, we were performing on only one audio file, but now we want to perform on the batches of audio files. So we're using Glob to find all the file paths that matches this specific pattern. Okay. Here, this code, it processes the batch audio files to extract and visualize their MFCCs features after we standardize them. So it's the same thing. We're just going to loop through each file, each audio file, and then calculate the MFCCs the same way that we did, and then we normalize them by getting the mean for each of them over the standard for each of them. And we're appending this normalized in MFCC batch list here. After that, we're going to do some padding. And okay, why do we need padding? So we know the audio files can differ in length. So one audio file can be like 10 seconds, another audio file can be 2 seconds. And then when we calculate their MFCCs, the MFCCs are going to be different as well. But we need them to be in the same length. That's why we introduce something called padding. So here we find the maximum length that we have, like the longest audio file. If it's 10 seconds, okay, we're going to say 10 seconds is our maximum file. Then we want to find, like if we have a file that is 2 seconds, we're going to take that file and then pad it with zeros until it gets to 10, or the MFCCs are equal to MFCCs of the longest file. We do that for each file until we have the same length for all of them. And then we just plot the same way we did, and we're plotting here two different audio files, just to see like it's better to compare this way between the audio files. Okay. Next, we do the same augmentations that we did, which is the time masking. Here, time masking, we're going to do it for batches, but we're using the same parameter. The length is going to be 100, but the probability is going to be 80%. And then we plot it again, and then, yeah, two plots just to compare. Then we continue on to frequency masking. Uh, yeah, so it does the same thing. We're just dropping some frequency here horizontally, and we can see it here also horizontally. Uh, so this we are done with the data pre-processing for the signals. From here, we learned how to calculate the MFCCs and the time and frequency masking augmentation techniques. These techniques are very helpful, as we said, to make the model robust to the noise and less sensitive. It will make it more accurate. Okay. Then next, we're going to see, okay, we're going to see the image preprocessing next. So, what is image preprocessing? Before training any machine learning model to understand images, we need to prepare them properly. So, why is it important? The real world images can be very messy, can be varying in size, they can have like different lighting conditions, they can contain noise. All of this will make our model perform very poorly. So we have like key pre-processing steps that we can use. We resize the images. Resizing the images is just making like sure all the images are in the same size, and so they can be like fed to the model, because the model usually expects a certain size. Uh, yeah. And then the normalization is the same thing. We can see the similarity about the pre-processing in the images and the pre-processing that we've done in the signals as well. Here we also do normalization, which is make a standard range, usually 0 to 1. It makes the training more stable. We also do augmentation. Here we have different kind of augmentations, like we rotate the image, we flip the image, we can do also scaling, we can do color jittering and all of that. We're going to see all of that. And also we can do denoising, which is reduces the noise and all the irrelevant details that we don't need. So why do we do data augmentation? Data augmentation help us to get more data to generate more training examples from the original data set. It also prevents overfitting because it introduce like diverse data set. So common augmentation techniques, as we said, rotation, flipping, scaling or cropping. Scaling or cropping can alter the size of the or the focus area. The color jittering, it adjusts the brightness, the contrast, and saturation. So we're going to all to see all of this in our code. So we start by importing the libraries as usual, the libraries that we're going to use. Then here so here, what we're doing here, we're making different directories, and then we are using curl. Curl help us to download data from the net, like from online. So we have three data files. Why are we doing this? Because usually the data set that you have when it's big is going to be structured that way in different files. So even though we have three images, we're just mimicking how the data structure usually is going to be in different files. Okay. So as we said, it's always easy to work with images when it have the same dimensions. That means that we will need to resize all the images that we just downloaded. We can just use the resize, like the resize, which is help us like resize images to the dimensions that we want. Okay, so here we're creating a function. The function is called resize image. We're using this Lacknose resampling, which is like it's a high quality filter. It's useful to resize the images without we like without loss of significant significant like quality of the image. Okay, these are the directories that we just created in the previous step, and this is the size that we want. We want all the images to be 22.4 by 22.4. Okay. And then here we're just we're like looping through directories. We're finding the images, we're resizing the images, and then saving them. Okay. Here we're defining the data directory. It's the root data directory without, it doesn't define like one image. It's just the root one. And then here we apply a transformation to tensor. So as I said, like it converts the images to PyTorch tensors, which is how PyTorch like processes the information. Okay, here we are defining like where we want to plot three images next to each other. These are the original images. As I mentioned, that it's always good to see how the raw data looks like. So these are the three images that we have. Then we can move on to our data transformation. So here we're going to apply normalization, and also we want to standardize the images. So here the first thing that we do is to calculate the mean and the standard deviation for each channel. So because we're going to use it for the normalization. Here we're defining like a function to get the mean and standard deviation for each channel in each image, and then it will return the mean as a standard deviation. Then we move on. Okay, we move on to perform our normalization. Why we do normalization? Because it just ensures that we have consistent intensity across all the data set, which means that it will remove the variations in lighting and the contrast. And this will help like our model to just focus on the more important features than getting distracted by things that it doesn't need, like the variations in the lighting and all of that. Yeah, so we do the normalization. We're also converting to tensors, and then we also want to plot. Here, this time we're plotting, as we see here, these are the pure images without any normalization, and here these are the normalized images with the normalization applied to them. So we are plotting both of them so we can see the difference. These are the normalized, these are the pure images, and these are the normalized images. As we can see that the lighting and construct is a bit different. Okay, after we're done with normalization, we are moving to data augmentation. Here, we're going to use different techniques for data augmentation. Um, this dot compose, like transform dot compose, this one, it helps us to apply multiple transformations at the same time. Uh, so here we're only, as you see, like I've commented all of these. Now we can just focus on seeing how the random horizontal flip looks like. Okay. So as we said, the data augmentation is like you're playing with the data that you have. You just flip it horizontally, you flip it vertically, you play with the colors, you do like resizing or just scaling. This will help us to get more diverse data, which will make the model robust. So let's see this horizontal flip, which as like from its name, it flips the image horizontally. Okay, these are the original images that we have. We just saw it. And these are the images with horizontal flip. We can see the difference, right? Okay, now let's try to do all these together. As we said, resizing, it ensures the images are all resized to the same size. Remember the size we wanted. And then we are performing horizontal flip with a proper probability of 50% because it does that randomly, so 50% is the probability. And then the color jitter, which plays with the brightness, the contrast, and the saturation. And we also have the random affine. So it keeps the image, it does some scaling to the image. Yeah, in simple words. And then we convert to tensors, and then we also can perform the normalization here. Okay, and all of this is for plotting. So let's see how it looks like, and let's see what kind of transformation we can spot. So from here, we can see that the color jittering, it played with the contrast and the lightening of the photos. And okay, this one has horizontal flip also. And this one has the affine. It has some scaling as we see in the picture. Um, yeah, and this one has some scaling as well, and we also see the color jittering. Okay, and if you can spot more, that's great. And okay, let's move on. This is just another example. We don't have it here, but we can do something called vertical flip. It's just like the horizontal flip, but it's done vertically. As we can see here, this is the original images, and this is the images with vertical flip. Okay. And here we left some questions for you just to test your understanding and your how like what did you gain from all this all the videos about data sets, the loaders and the data preprocessing. Okay, thank you for watching the video and I hope it was useful.